All right. This should look somewhat familiar from your e-homework.
You're probably wondering why we like that.
Not exactly the same, but relatively close.
Yeah.
Well, can we make it exactly the same?
And can you add a mass to it?
Where do you want the other mass?
No, I mean add a mass of the actual broom or whatever that
Yeah, this thing is 500 newtons.
Oh, okay.
Okay? Now, in your problem, do they give you mass or do they give you weight?
They give us mass, I
They
think.
give you mass?
No, they give us force.
They give you the weight?
Yeah, they give us weight.
Yeah, it's
Just be careful. If they do give you a mass here, then you remember you had to turn that into mg, right? You had to turn it into weight. All right, first things first. Well, here's what I want to know. I want to know what's the tension in this cable. Okay? We have a 4-meter boom
I know, I hate that.
held up by a cable. The boom is holding up, like it's like a crane, holding up 1,000 Newton weight. This boom itself here is 500 newtons, and it's connected to the wall here by a pivoting joint. Okay, so it can be raised and lowered. All right? So I want to know a couple of things. I want to know what's the tension here, and I want to know what are the forces at the wall. Okay? So find out the horizontal and vertical components of this force, and then we can find out what the total force is from the wall. Okay? All right. So,
Angle?
The ankle?
and then, oh yes, we do need to know the angle. Thank you.
I didn't even know what
Let's make this angle here 45 degrees. Okay? All right, so when we have a problem like this and we're looking for tension and we're looking for forces at the wall, where do we start?
do the free body diagram.
Yeah, where do we always start? Yeah, when we're looking for forces, we're almost always, it's never a bad idea, and it's almost always the best idea to start with a free body diagram. So everybody, please draw the free body diagram of, well, what?
The boom.
Just the boom? Does that sound good?
Well, I mean, you're gonna know the forces. Yeah.
All right, if we draw just the free body diagram of the boom, then that will incorporate all the forces we're looking for, right? And it'll be a nice simple drawing, so let's do that. So here's the boom. Nice simple drawing. Okay, forces. What?
Tension going that way,
Okay, tension going this way,
perpendicular.
and it is perpendicular. And it's important we put it at the right spot.
1 meter.
Okay, so we got 1 meter right here, and we got 3 meters right here. Okay, the weight.
Of the mass and of itself.
Okay, we've got a weight right here going straight down of 1,000 newtons, but we also have another one from the boom itself, and that will be from its center of mass, right? So we have to locate the center of mass. We assume that's going to be in the center, since it's not given any other information, and that's only 500 newtons, but that will not be at 3 meters, will it? So let me redo this. Let's make this 1 meter here and 2 meters here. So we got 2 meters here, and then a meter here, and then a meter here. Does it look good? Okay, what else do we have? Any other forces?
Yeah, the pivot.
Okay, we got stuff going on at the pivot. Will there need to be a horizontal component to that force at the pivot?
Yes. You could. Yeah, you have to.
Yeah, why do we know we have to have a horizontal component?
Because it's against the wall, yeah.
Well, not just because it's against the wall, but from our diagram it tells us why.
tension's pulling left, and we need something.
Yeah, because see, look, if we split these up, and let's say all the verticals are purple, and then this one is both horizontal and vertical. So we'll make our horizontals yellow. So these are the components of my tension, right? So I've got this up and these two down. So there's no real indication yet that there needs to be a vertical force here, right? Because it's possible that these two could cancel that one, and we could be okay, right? Because it's stationary. You know, we didn't really talk about that, but that's a really important step. It's static. What does that mean? What does that mean in physics?
Not moving.
Okay, not moving.
Rotation.
What else does it mean?
You can pick your point of rotation.
Okay, you can pick the rotation point anywhere you want. What else does it mean? Does the velocity stay zero?
Yes.
So what's its acceleration?
Zero.
Zero. If the acceleration is zero, what does that mean?
No more. Net
Ah,
zero.
all the forces cancel out. Oops. That means the forces in the x add up to zero. The forces in the y add up to zero. And over here I'm going to write the sum of the torques must also add up to zero, right? So rotational stuff I'm over here, and translational stuff I'm right here. And we call this, whenever we have this and this and this, then we say the object is in equilibrium, right? It's in static equilibrium in this case. So static equilibrium. All right? Very important. So whenever it's static or it's in static equilibrium, then it means all that stuff all at the same time. Or if somebody says, well, the acceleration is zero, then it means all that stuff at the same time as well, right? So we know that these purple vectors, all the ups and the downs have to cancel. And so these could cancel. We don't know if we have a vertical one over here or not yet. Do you think there's going to be a vertical one over here?
I think so.
Yes.
Common sense tells you that there at least might be one, right? Which way do you think it will be? Up or down? Think up? Okay, so let's draw it up. All right?
And the horizontal.
But we know for sure there has to be a horizontal one, right? And we know because if that's our only horizontal force, what's the object going to do? It's going to zip that way, right?
Through the wall.
Yeah, through the wall. And we know that's not going to happen. So which way is our horizontal force going to have to be?
That way.
It's going to have to be to the right.
And equivalent to that one.
Yeah, and we know that this one equals this one. So we already have an idea of how those are related. In fact, we'll go ahead and write that down. Okay? This equation right here tells us the sum of the forces in the x direction. Oops, I pointed the wrong one. That one. Equals 0. That means that h must equal tx, or h equals, see, this is going to be 45 degrees, right? And since it's 45 degrees, I could use, technically I could use sine or cosine, but since I marked that angle, then it would be t cosine 45, right? I know this to be a true statement, right? But I just don't know what either t or h are yet, right? Okay. Can I write this statement? Will you please write this statement for me? What do the sum of the forces in the y adding up to 0, what does that look like? 1,500 newtons.
Equals T sine 45 plus V.
There you go. So the ups equal the downs, right? That must be true. So we got that as our true statement. All right? Now, unfortunately, we still have a problem. We can't solve anything yet. Why not? Yeah, because let me circle the unknowns. I got an unknown here, I got an unknown here. I got an unknown here, and I got an unknown here. Well, I got T, H, and V are all unknowns. This N is just the unit over here. So I need another equation. So let's use torque. We have one left. So let's say that the sum of the torques equals 0. All right, now, Colin pointed out that, look, we can pick our pivot point anywhere we want because it's a static problem. Now, when we get into Physics C next year, then if the object is actually rotating, we will have to use the actual rotation point. But since it's not rotating, we can pick it wherever we want, because if it's not rotating about the real pivot point, it's not rotating about any point at all, right? So we can pick any one we want. So let's use our gray matter. where would be some really good places to pick the pivot point?
The end.
The actual to the.
Actual.
The actual pivot point is the one most people are at. Has anybody said a different point?
The top.
You could choose.
You could choose this point if you wanted. If you chose that point, we would eliminate the torque from this one, right? But we'd still have these two torques, right? And these two torques are going to be at angles, which is going to make it really messy, right? So I agree. I think the real pivot point in this case will eliminate both of these unknowns because they'll have a radius of 0, right? And so therefore it makes my problem as simple as I can get it. And that's what we want. Okay? We call that an elegant solution. Elegant solution means I'm lazy and would like to do it as simply as possible. All right? So we want this as elegant as we can get.
So I'm very elegant.
Quite an elegant young man. All right, so now here comes the first hard part is picking your pivot point. So we figured that out. Then we got to figure out,
The radius.
well, we got to figure out which torques. Torques this way or torques this way? Clockwise or counterclockwise? Okay, so let's label them. And I'll make the clockwises green and the counterclockwise blue. So which ones of these are going to give you clockwise torque?
The 1,000.
The weight.
Okay, this one and this one give you clockwise torque. Okay, these two give you nothing. And then up here, do I want to use the purple one, the yellow one, or the maroon one? I want to use the maroon one. That's the total force, right? And that one's going to give me a torque this way, right? It's going to torque me back around this way, counterclockwise. So, until you get a good feel for this, you might want to actually write this down. When this is true, that means the sum of the torques clockwise must equal the sum of the torques counterclockwise, right? Because some of them are going to be positive, some are going to be negative. Now remember last time we talked about the direction of the torque. Clockwise torques will give you a vector into the board, right? Technically that's a negative torque. Counterclockwise torques will give you a torque out of the board. Mathematically, out of the board is positive. So technically you would have a positive torque and two negative torques that'll add up to 0. But it's easier for most people just to separate them. Clockwises must equal counterclockwise. Does that make sense? All right, so let's start with clockwise. What goes here?
The radius.
Okay, it's going to be, remember, torque equals RF sine theta, right? Or RF
Perpendicular.
perpendicular.
Which is what we need.
Okay, and also it could be R perpendicular times F, but we generally will use one of these two most of the time. All right? So, let's start with the 500. Radius,
What do we say? 200.
2 meters. The force,
500.
500 newtons.
But it's
Okay, angle.
perpendicular.
Okay, let's find the perpendicular part. So if okay, the perpendicular part would be this part, right? And for us, that angle right there will be 45, right? Can you see that? 45? So, why? Because this angle is 45. And you know what? Here, let's do it the easy way. It's a little bit harder to explain that one. Do you see that this angle is 45? Alternate interior angles? Because you got a line like this, split like this, right? So these two are the same? Okay, when you draw a perpendicular in here then if this is 45 and that's 90, that has to be 45 as well. Now your problem has a different angle than 45.
Yeah.
So just be careful, okay?
So that one actually matters which you choose. Something like this.
Yeah, it does matter which one you choose because your sine and cosines will be different. So if I choose this one, the perpendicular part will be this side, right? Which will be the sine side. So I will use sine in this case. sine of 45. All right? Plus, that's only this one. Now I got to do this one over here. So what's my radius? 4 meters. And then 1,000 newtons. And then, once again, this is 45. And so there's my perpendicular side. So I want the sine again. Sine of 45. All right, so I took care of these two now. Those are both my clockwise. So let's do the counterclockwise now. Okay, radius would be 3 meters, right? Here to here. And the force is tension. And then do I have to worry about an angle?
Nope, already at 90.
Okay, I'm already at 90 degrees, right? So I'm good to go. I'm already at the perpendicular. So there's my equation. Now that one is substantially harder for students to do the first few times through. Okay? Substantially harder. So make sure you take your time and don't skip steps. Okay, if you skip steps, you're going to miss something. All right? So
Why is it just tension?
okay, it's just tension because this force here, it's R times F perpendicular, and the tension is already perpendicular. So we're good to go. So right here, this is my force perpendicular, right there, right? Okay, so the rest is just math, so help me out here. What do we get for tension? 1179-ish?
Yeah.
Yes.
Okay. All right, after that, that's by far the hardest part. Once you get that, you can plug tension in here and here and get the horizontal and vertical part, right? So, do that for me quick, just so we have them. Okay, what do you get for horizontal?
833.
And what do you get for vertical?
Oh my God.
No, it's
666.
It's 666.
Whatever.
No, it
No, don't put it, don't put it,
You gotta
don't
put
put it.
that down.
It's
Hey, look at clown.
That's the answer.
6 rounds.
Don't erase it. That's what it is.
It is what it
Not
is.
like no one's writing on here.
That's not what it is, bro.
Writing on your arm or anything. Okay.
Actually, hold
Hey,
on, give me a
now, I have a question for y'all. If we had picked this vertical one, because we weren't sure which way it went, right? So we just picked up, because it seemed to make sense. What if we had picked up, but our answer came out to be negative? Yeah, that just meant we picked it in the wrong direction. No big deal. Just means our arrow wasn't right, it's going to be the opposite way. Okay, so if you ever run across one of those, no big deal.
That would be
Oh.
bad. That would mean the beam is holding up the wall, like that's holding up the wall.
Actually, but what's surprising though is if you have a problem like this, so like this, and the vertical force in this particular case is down, right? And what will happen is a lot of students will pick up because it seems to make sense that up would be the force on the right, and so they pick up and then they get a negative answer, and they're like, oh, I got it wrong. Well, no, you didn't get it wrong. You just picked the wrong direction to begin with. Everything's okay. All right? So sometimes you do have to push down on the beam.
Well, yeah.
But in this case,
yeah, and this would be very weird because the beam is being held.
yeah. In this particular case, it's
That would mean
Yeah,
the
pretty-
tension would have to compensate for the wall too. I mean,
yes,
which would be very bad.
yes. Now you can get some angle when you lower it down. You'll eventually reach an angle where there's no vertical force from the wall, because eventually you'll get to a spot where the wall will have to push down at some point. As when you lower it down, eventually you'll have to spot. And
This will
so,
be very efficient.
so that, a really hard question, challenging question would be: at what angle is the vertical force 0? One last thing. In reality, this is one force. This is just the horizontal and vertical components
Of the
of the force from the wall. And so what happens is you could really add these two up to come up with what the net force is. Okay? I didn't ask you for that, but just in case you ever see that, the reaction force from the wall is actually these two Pythagorized. Okay? All right, you ready? Okay, 40 is right here. All right?
And
Here's a 100-gram weight.
that's essential.
How far out can I put the weight? And it not tip over?
It's whatever revolution per second.
What do you say?
What's the mass of the meter stick?
How far out can I put this weight and it not tip over?
Bad, Mr. Bruce. Drop the weight.
So if I put it out here,
You know it's falling.
doom. The question is where exactly can I place it and it not tip over? All right?
Can it move or it has to stay completely stationary?
Well, it'll be right at the balance point. Okay. So Colin asks, what is the weight of the meter stick? All right?
We should go loud for this.
No,
Meter
you
stick.
shouldn't.
So it's a bit more complicated.
We're probably already done our point.
Meter stick is 134 grams. That's the mass of the meter stick. Okay?
What's the mass of
And
the
the weight
mass?
was 100?
And the mass of the mass is 100. Mass equals 100 grams. Okay? All right, we draw a free body diagram.
Bum, bum, bum.
There you go, meter stick. Now what do I do with the free body diagram?
You put normal force.
Ooh, ooh, ooh.
At the center.
Now, we do have a center of mass right here, and that's going to be mg, right?
Your
A meter stick.
Ooh, we're going to have a fulcrum, right? Where is the pivot point going to be? Yeah, over here at 40, right? So that's 40 centimeters right there. Here's 100 centimeters. Here's 0 centimeters. Okay?
Which one's it doing? That's the mass of the meter stick.
He's doing.
And that's the mass of the meter stick. So that's going to be 0.134 times 9.8. Okay, where's my mass going to be?
On this side.
Somewhere over here.
We're finding this. You already have this.
That's what it's on.
You're finding the force of the
Now I
wall.
guess find the tension.
Of the wall.
Oh, that's.
You know, the whole thing.
All right?
Oh, the tension.
Now, there's a force up right here. This force up is the normal force. How big will that normal force be?
the sum of the weights.
Yeah, whatever these two add up to be, right? Now, the normal force is all going to be right here because that's going to be where it's going to be pivoting about. When it's just about ready to tip over, it's going to be pivoting right there. Okay? All right, so what do we do now?
Equation.
The sum of the torques equals 0, right? I got a clockwise torque here. I got a counterclockwise torque here. They must equal. Hey, you know what? Am I going to have to worry about the 9.8? That's going to disappear, right?
Yeah.
Because we're going to end up with a radius force and a radius force. They're both going to have a 9.8 in them. I'll put it in just to show you. But all right, so what's my radius for this one?
10 centimeters.
10 centimeters. And the force is 0.134 times 9.8. And what about the angle?
90.
90, so 0.
90, so sine of 1, right? So we're good to go. All right, that one's got to equal the one on the right. What's the radius for the one on the right?
We don't know. Solve the force.
Question mark. Question mark radius. and its mass is 0.1009.8 times, and it's 90 again, right? So my 9.8 disappears. And notice that my answer is going to end up in centimeters, right? Because the grams or the kilograms here. Hey, did I even need to worry about putting it in kilograms? I could have left it as grams and grams, right? And we'd have been okay because the grams would have canceled. All right, so what do I get for question mark? 13.4 centimeters. Okay, now talk to me here. Does that mean I place this on 13.4?
13 from 40.
From 40.
Ooh, so where do I place it?
So
From 15.
53.4.
26.6 from the.
Okay, so if this is 13.4, and this is 26.6, right? So I place it on 26.6. All right, let's try it. Put this right here on the edge. 26.6.
Still has a
Now move it a little bit to the left. I mean right.
You're right.
Move it to this side. I'll put it on 26. There
That
you go.
was too fresh.
All right, so here's your assignment: is to get an 8-foot long board, set it on a rooftop, stick it out a ways,
At one of those
And then
nice,
jump on the ice.
yeah, and calculate how far out you can go.
not very.
Not calculating.
No, we did a test though.
Experiment.
There's our experiment, right? Just walk on
Do you
out.
mind if I?
All right, next question. Oh, it's not balanced. Okay, I've got a wheel like this. All right. Actually, I have a wheel like this. I have a wheel. And like this.
I have this wheel.
I have this wheel. Thank you. I have,
This wheel is mine.
and I have it. All right. So here's a wheel. How's that? Okay. If I attach a 5-pound weight here, okay, I just clamp it on. If I attach a student here, all right.
Then it's maybe a light student for you to keep
Okay.
holding.
We have
Sir
a
Isaac Newton on
we
there.
have a
Pound guinea pig.
5-pound guinea pig holding on right here.
So we should try it.
Okay? And we have the 1-pound hamster right here.
A what?
A 1-pound hamster right here.
Gerbil.
Sorry, gerbil.
Can we change this to?
Hey.
Okay, we can change it to kilograms if you like. It won't matter. Okay, so 5 kilograms. That's really heavy. A really fat 5-kilogram guinea pig right here.
It's the original.
And gerbil.
Gerbil on that side.
And a 1-kilogram gerbil
Still
here.
heavy.
Okay? My question is then, right up here, how much weight, what size animal do I have to attach here so that's in equilibrium?
And what kind of animal?
More
That's
than
right, and what kind of animal? That's for bonus.
Everybody knows what's being done.
First of all, it's wrong.
Okay.
It's in kilograms, stupid.
So let me draw it again. So I don't know if I can draw a guinea pig.
So is it a 45-degree angle that this strange new animal is at?
Looks like a woolly worm, but it'll work. Okay, 5 kilograms. And then over here,
He's at the very bottom of the shelf, like it's ready.
this looks more like a mouse probably, but 1 kilogram here.
Is it a 45-degree angle?
Okay, right here,
Oh, that's right. Yeah, it's 9.8.
this is 30 degrees.
That is just not fair.
It's a pelican? All right,
That's the next animal.
what animal needs to be attached here, and what's its mass?
A bajillion.
Yes, you must know the animal. All right, set it up. What's the first thing we have to do?
Free body
Solved.
Free body diagram.
diagram.
Okay, so here's my free body diagram. Hey, I'm gonna have 5 times G here, right? I'm gonna have 1 times G here, and I'm gonna have,
Question G. Question G.
yeah, question mark times G here. So do you see that the G is gonna cancel out in each case when we do our torque problem? Okay, so there's my free body diagram. Okay, what about pivot? Pivotus. Center. I like that. Center. Okay, so what kind of torques do I have?
Clockwise again.
Counterclock them and clock them, right?
Clock 'em.
All right, so these are clockwise, and this one's counterclockwise, right?
Yeah.
Okay, so let's see if you can get it.
They are now.
How do you? Because it's facing that way.
What, counterclockwise? Hey, you know what? This is always a common question among students. It's like, I'm having trouble, why clockwise, why counterclockwise? Here's how you do it. It always works. Get your pencil. Take your pencil, stick it right here, or pen. Hold it at the pivot point, and then apply the force. Ah. Counterclockwise.
And then remember which way a clock moves.
Oh,
And then-
wow.
Clockwise. Clockwise, right? And that's kind of it's a nice, easy, tactile way of figuring it out.
You don't know.
But of course, you always still have to realize which way is clockwise and counterclockwise, right? No, that's okay. So you can see it's rotating that way then, or the other way, right?
I'm assuming we get.
All right. Sum of the torques counterclockwise equals sum of the torques clockwise, right?
Yeah.
So counterclockwise, I've got a big radius of R and a force of, what, 5G, right? Okay, and then do I have to worry about an angle for this one?
No.
Okay, I'm perpendicular, so we're all good. Okay, over here, let's handle the easy one first. It has a radius of R. It has a weight of 1G. And once again, we're good to go on the angle. Okay, so next, we have another one clockwise. It has a radius of R. It has a weight of unknown times G. And we do have angle to worry about. So,
Jeez, gravity.
what angle do you want to use? Do you want to use this angle? It's okay, 30? That's an easy one to find. So when I use 30, how do I use that to get the perpendicular part of the force? The perpendicular part of the force would be this part, right? So that would be sine again, right? We okay with that?
Yep.
So it would be sine of 30. So notice that G goes away. Notice that R goes away. I'm left with 5 equals 1 plus question mark sine of 30, which is 4 equals question mark sine of 30, which is 8?
Yes.
8 kilograms. Now, let me show you why this whole perpendicular radius thing comes in handy. Okay? Because this is radius times the perpendicular force right here, right? But we could have solved this easier if we'd have thought about this as the perpendicular radius. It's not 8? What is it?
You forgot your G. That's 8 newtons.
Oh. No, that's right. The G cancels out.
Yeah.
I'm left with 8 kilograms. Isn't that right?
Yeah.
Okay.
I think that's right.
It is.
I didn't see if you had your G.
Okay, look everybody.
We're trying to find it out. It's like 20 pounds.
What weight I have to place there? What mass?
It's like
The cosine component of this is along the radius, right? The sine component is
Perpendicular
perpendicular.
to the radius is what.
You want to be perpendicular to the radius.
My largest
That's
hat
the
was
power.
Perpendicular to the radius. Hey, everybody, look at this though. What if hey, shh, let's look. What if I would move this mass down to here? Look, here's my minimum perpendicular radius. If I move this mass down here, wouldn't it still be at the same location producing the same torque?
Yeah.
Yes. And what's its radius now?
Half hour.
1/2 r. Hey, guess what? What's sine of 30? 1/2. So what I could have done here instead is said, look, instead of doing the radius times the perpendicular part of the force, why don't I just do the perpendicular radius times the full force? That would be 1/2 r times question mark g. And I get the same answer.
So R is equal to go away. 1/2 R is equal to 4. So yeah.
So you get the same exact answer. So the answer is 8 kilograms would have to be placed there. All right? So obviously a cat, right?
That's fluid.
Fluids. Okay, name me a fluid. Water.
Oxygen, yeah.
Milk. Gas. Ooh, O2. Gas. There we go. Okay, we're in good shape because a fluid can either be a liquid or a gas. Okay, now, everybody, we've already talked about some of the extra special properties of gases. Gases have some properties all their own. PV equals nRT, and what? Delta U equals 3/2 nR delta T, and all that stuff we learned about for gas laws.
Yeah.
All that stuff about kinetic theory of gases and the molecules aren't connected together. It doesn't have a specific volume. All that stuff, right? So these are only for gases. Now we're going to talk about the commonality between the states of matter that flow. Okay? Fluids and gases. Even though they have very huge differences, they have a lot of things in common. Okay? And so what we're studying now is the commonality between gases and liquids, called fluids. All right? Now, when we study fluids, we're going to study two separate things in fluids. We're going to study static fluids, what happens when the fluid is sitting still and not moving. And then we're going to study a little bit about dynamics. Dynamic fluids, okay? So static fluids and dynamic fluids. Most of the questions you're going to run across will probably be static fluid questions, but you will run into some dynamic fluid questions. But dynamic fluid starts to get really complicated really quick, so we're going to only learn a few basic properties. All right, so let's study a few things first. Okay, before we get into static and dynamic fluids, we got to study some background stuff. Background stuff like, you need to know what volume is.
Whoa.
Can you get it? Can you get it? What's volume?
Understand. I don't know.
Volume is what they put on anything.
It's too complicated for me. You need calculus to do that.
All right, volume. Okay, unfortunately for us, well, volume is length times width times height. Hey, please remember that it's also, like for a cylinder, equal to area times the height, right? Just don't forget that. That comes in handy. Also, please don't forget about volume. What units for volume?
I got a lot of them.
All right.
Okay.
All right, will you please calculate the volume of that rectangle?
Rectangle. That's not a rectangle.
A rectangle doesn't have, it's zero. Rectangle has
Which rectangle are you talking about?
Taste.
Please calculate the volume of that rectanguloid.
Two centimeters. Oh, cube.
It's got to be in meters cubed, please.
Oh,
No, it's getting all,
lots of
getting all
zeros.
unity on us.
Meters.
2e to the negative 6. That seems so.
0.000002 meters cubed.
Okay, is the answer
no.
Add a lot more zeros.
It's .00 square.
I didn't watch
Add 5. Well,
All right.
add 4 zeros.
Okay, excellent. What I want you to avoid is this. The problem we have sometimes with volume is that students go, oh, I got to convert that to meters cubed, and they do this. 1 meter over 100 centimeters, and they get 0.02.
That's centimeters squared meter.
Yeah, that is exactly correct
It's centimeters squared
in the proper
meter.
units. That is 0.02 centimeters squared times meters.
Can we do it on AP test?
No. Well, yes, but no.
In response, you could.
That is absolutely correct, but it's most likely is a grader won't catch that, and so they'll count it wrong even though it's correct.
They should get fired for that.
Okay, you got to do that 2 more times, right? So it really is 0.0000002 meters cubed. All right? Okay, make sure that you convert it 3 times, right? I just don't want you to mess that up on an exam and get a crazy, crazy answer. All right? All right. Let's talk a little bit about mass density. So we've talked about volume. Okay, mass density. Density.
It's a tie.
It's a tie.
All right. Symbol for mass density. Excuse me. Hey, what's your symbol for mass density in chemistry?
We don't even know.
Is it D?
Density is D, mass is M.
The units are in
No. Well, okay. In chemistry, I don't think you use the same symbol we use. In physics, you use this symbol. It's the Greek letter rho.
How do you spell that?
R-H-O.
She's the pregnant?
She hasn't got the baby.
It's rho. It's the Greek letter rho. It looks like a 6 flipped over.
We'll say that. Like a 9.
Or a 9, mirror image of a 9. But it's a small case letter. So it's like, you know, it's like a P. So the tail goes below the line. All right? Yes. So when you write it, it would look like, you know, 1/2 rho V squared. If the V is volume, right? So the rho is a lowercase letter. Okay? V, volume is capital V. All right, now, everybody. Mass density, Greek letter rho. Mathematically, what is it? What's the definition?
Mass over volume.
It's the mass over the volume. Okay, so units on that are going to be kilogram
I figured that.
per meter cubed. So kilogram per meter cubed. That's our unit. That's the physics unit. Remember, physicists are really sticky about their units, and they want to keep 1 unit for everything. Rudy, less talky, more lissy. All right, now, when we do density now, it's going to look a little different than chemistry. Because, like, what's the density of water in chemistry? Oh, you got to remember that.
That's what we never cared about.
Yeah, it's 1.
Specific concept.
Yeah, 1.
But 1 what?
Gram per milliliter.
Gram per milliliter or gram
Or centimeters cubed.
per centimeter cubed. Now, if you do the conversion, actually, everybody please, convert that into kilogram per meter cubed, please. And go. 1, 2, 3, go. What's the answer?
I didn't 5th grade. we did.
0.001. Does everybody agree with that?
This is Jonathan,
It
guys.
repeats itself.
I don't think so.
I will work it out.
Yeah.
I didn't like
What'd you
that.
get?
We got 1,000. Anybody else?
That's what I got. I don't know how I got that.
Wait, yeah.
Did you,
I got a
I
thousand.
think I did get it wrong.
So what are we?
It's
I think
fifth
you
grader.
did.
Yeah.
All right, 1 gram per centimeter cubed.
Because it's over.
Okay, everybody, shh. Come on, we've done this many times before, and you all are slackers. You're all trying to do it in your head, and you're all trying to take shortcuts. Do it right.
We did do it right.
No. Well, somebody.
Well, then how-
All right, grams down here, kilograms up here. Which one's bigger?
Kilo.
How many grams are in a kilogram?
1,000. So it's 0.001 kilogram.
Okay, that takes care of that. Okay, centimeters. I want centimeters up here and meters down here.
Cube.
Which one's bigger? How many of these make up that?
100.
But I gotta cube it.
And that.
So I end up dividing by 1,000 and multiplying by 100. Choked. 100 cubed. I choked on my 100 cube. What do we get? 1,000 kilogram per meter cubed. Don't be a slacker. Come on, do it right. Do it right. Okay, so everybody, you must know the density of water in physics. All right, that's one of the ones that they will expect you to have memorized. It's nice and easy. 1,000
Kilogram per meter.
1,000 kilogram per meter cubed.
0.001.
You have to memorize that. So this is not correct. No, 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 no. This one's correct here. In fact, we're never going to use 1. Never, never. 1,000 kilogram per meter cubed.
Why can't chemistry and physics just agree?
Well, the reason why
Because they're
physics
both
and
jokes.
chemistry don't get along that way is the same reason that, say, when you drive a car here, the speed limit's in miles per hour instead of kilometers per hour like it is in Canada and Mexico. The reason why is
And the rest of the
because,
world?
yeah, the rest of the world, is because of the way that physics and chemistry began as separate sciences. And so chemistry began as an experimental science. Physics began more as a theoretical science, and so it was easier in physics to keep your units just one unit. And in chemistry, if you're having to measure lots of different things, it's better to have useful units, right? So that's why in chemistry you can have all kinds of different units, and it's all good. But in physics, they like to have one set of units because for them, that's all good. This is the mass. This is, oh.
Again.
Twice.
I ran 400 to
Oops. This is the mass. And this is the time.
I like the.
Okay, if you're in the English system, your
Is it a
weight,
I love it.
weight is a standard unit.
What?
So over here, this is newtons, right?
Oh, yeah.
In the English system, this is pounds, and things are defined by pounds. Okay? So pounds, seconds, feet, and slugs.
What?
Oh my god.
Your mass is in slugs.
Yeah.
Collect all these slugs and like then just compare you.
Yeah.
What happened like the torque? that
Why
was-
is the unit putting out LB for pound? Is it for the loaf of bread that is supposed to weigh 1 pound?
I have no idea where that comes from. That's a good thing to Google.
What?
I don't know. Maybe I'll Google
What's a
it.
slug? Like, how many grams is that?
A slug is
It's one of those things, you
32.2
know, that
pounds.
was slime all over. One of those.
No.
You salt it,
pounds
Yeah,
on
it's
Earth.
like metal.
So it's a big
Metal.
thing.
salt it, you know.
All right, yeah. No, you don't salt it. Bad.
I do. I salt it, toss it in the trash.
All right, here we go. Quiet, quiet. Now, when we're talking about density, we're talking about density. Quiet. We're talking about density. Liquids will have a substantially different density than a gas. All right? We'll go from liquid water right here. If they have something else, they'll have to give it to you. But mercury, Hg, right?
You know
So
that.
these are things you have to remember?
No.
Oh wait.
Just that one. But you will run across mercury from time to time. A lot of times they'll do a problem where you're in salt water. Salt water is H2O plus salt. Is about 1025 kilogram per meter cubed. Salt water is a little more dense. All right. So they will give you the density, but you will need to know this one. Now, density for air. Okay? Density air. 1.29.
The only one we
Kilogram
have
per
to
meter
remember,
cube.
though, is water, though, right? That's the only.
Yeah, the
one.
only one that you have to know, memorize, is water. Okay, 1.29. Okay. You've got till the end of the period. Please calculate what is the mass of the air in this room. Go.
You have to find volume.
We'll do it quick.
Come on, let's do it. I'm Mexican. I do this for a living.
I'm guesstimating.
I got my measuring tape.
Volume of the room. You need the volume of the room. Quick.
Okay, here's the plan. I'm gonna bring a giant hose. We're gonna fill it up on the water tank on the inside.
Do you have a measuring tape?
Dear God.
All right.
Yeah, lazy.
Approximately 3 meters tall.
Okay, what about long?
Mr. Berman, I calculated to be 1 Chris.
All right.
Defined as the area.
Pace the room off. What do you get meter sticks out for? Just pace it. Just pace it off. Can somebody walk in a meter?
Can we just measure the guys?
Can I?
Ooh, you could measure the tiles.
There's 20 going
Ooh, smart.
Isn't that the first
I already
thing?
said I'm guesstimating.
That's right.
Guesstimating. I hate that word. Yes, I don't know how many goes.
It's 1 Chris.
You always say that.
I'm saying 1,161 mass.
I'm a chemist.
Okay, what is it?
I got 1,161.
You can't go yet. Step down.
We can't go.
Yeah, some of us are broke.
I'm not enough newtons.
See, I got it, 15 meters, 20 meters, 3 meters.
How many meters?
I got
This way, 40 this way.
How many meters?
Each thing is a foot.
How many meters this way?
How much is each?
No.
What?
Ah, you can't do it yet.
1 foot? You have to convert to meters. 49 feet.
1, 2, 3. How many? Sit down.
Hey, it's 30.5 and there's 40 of them.
So 40 is 9.35.
Yeah.
All right, so everybody, that's your assignment. Calculate the mass of the air in this room.
40 and 0.35. 3 and 9.
It's 1.4.